Hello everyone and welcome to today's webinar on part 1 MV cable test and diagnostics application and tools. My name is Sanjay Yadav and I'll be hosting this session today. Speaker for today's session is Mr. Xavier Ruiz, who is an area sales manager for CFL test and diagnostics at MEGGER. Also on the panelists we have Mr. Mohammed Saleh at MEGGER Middle East, who will assist for the Q&A session. So before handing the mic to over Mr. Xavier, I would like to highlight a few points. You all are being muted. To avoid any disturbance during the presentation, do park any question you may have for the Q&A session at the end or share it in the chat window. All questions will be answered at the end of the session by Mr. Mohammed Saleh. We have come up with an exclusive MEGGER Middle East page on Facebook and LinkedIn. So I'll just share that in the chat window. You can go through the link and you can follow us and like us and comment on the post and for regular updates and for engagement. We also have a lot of upcoming webinars in Feb, March and April. You can go on this link. I'll just share that in the chat window. So you can go through the link and register yourself for the upcoming webinars. There will be a small survey form at the end of the webinar, so please do fill the same for the feedback regarding the webinar. The recording of this webinar will be sent to in 2 working days to the GoToWebinar system as a standard process. I now hand over the control to Mr. Xavier. So let's get started. Over to you, Xavier.
Thanks to everyone for attending today's seminar. Let's start doing a quick review of the agenda for this short 15 minutes presentation. We will go first through the basics for medium voltage cables, and we will analyze what is the VLF test, the parameters, and the goals. Also, we will do exactly the same for the 10 delta and the partial discharge test. We will see what those tests are and what parameters are involved and what are the goals of the three test methods. Well, let's start with the basics for medium voltage cables. We are seeing in the slide the classic single phase cable in which we have a center conductor that could be of copper or aluminum material. Then we have this inner semicon layer. Next, we have the main insulation of the cable. We will continue with the outer semicon layer. Then next we will have the neutral concentric shield of the cable, and finally we will have the jacket or sheet of the cable. Regarding the constructions of the cable, besides the previous one that was the single phase shielded medium voltage cable, we can have the 3-core cable in which we have 3 conductors and each one with its individual shield. And also we have the belted cable. In this case, we have 3 conductors, but we have a common shield. So this is the different cable constructions we can have in medium voltage cables. Regarding the insulation for medium voltage cables, we have the solid dielectric or the polymeric insulation. You can see in the left of the slide the EPR and the XLP insulation, the XLPE insulations. They are maybe the most common insulations that we have nowadays in the medium voltage cables. And in the right, you will see the paper insulated cable. That is also, we can find them also very often in medium voltage installations. In terms of the faults for medium voltage cables, we should distinguish between local issues and global issues. A local issue will be restricted to a portion of the cable insulation or its accessories. And mainly, the local issues are related with poor workmanship or installation problems. By the other hand, the global issues are spread along big segments of the cable, and they are related with the aging conditions of the insulation of the cable. So depending on what problem we are dealing with is the test we will choose. For instance, if we are dealing with severe installation or manufacture issues, we can use the VLF test. If we are looking for incipient installations or manufacture issues, we can use the partial discharge test. And if we are looking for all cables and we want to know which cables are the oldest in my population of cables, we can use the 10 delta test. So depending what we are looking for is the test we need to choose. What is the VLF test? Let's start talking of VLF test. The VLF test is fundamentally an AC over voltage test. It's also called AC hypot. And the frequency we use for this AC over voltage test is 0.1 Hertz. In the VLF test, some standards allow to decrease the frequency. Some other standards don't allow to do that, okay? But well, normally we will say that the official frequency for the VLF test is 0.1 Hertz. And the VLF test is pretty much like a pressure test. And we will apply a voltage above operating. The voltage will be prescribed by a standard, for instance, the IEEE 400.2, and we will look for a breakdown. What we want to do during a VLF test is convert in fault the severe issues in the insulation or the accessories of my cable. We use the VLF test as commissioning test or after repair test, and is a go, no go, or pass fail test. So we will have a limited diagnostic information during the VLF test. The parameters involved in the VLF test are the wave shapes. We have mainly two wave shapes: the sine wave shape that you can see in the graphic in the left, and in the right we have the cosine rectangular wave shapes. Of course, both technologies, both wave shapes have advantage and disadvantage, and maybe we'll go through them in the next slides. The test voltage that we use for the VLF test will be between 2 times U0 and 3 times U0, where U0 is the rated RMS phase to ground voltage. And the test time will be between 30 and 60 minutes if we are using, for instance, the IEEE 400.2. The frequency must be 0.1 Hertz, but in the VLF test, we have the option to decrease the frequency. For instance, when we want to test very, very low cable with sinus units. The goals of the VLF test are convert in fault a severe problem in the cable insulation and its accessories during the test time, and at lower energy in comparison with the service fault. So this is very important, and we will do this under controlled environment, and we will avoid, of course, collateral damage. Now let's continue with 10 delta test. What is the 10 delta test? Well, the 10 delta test is a global method of testing cables to provide an estimation of the remaining life expectancy of the insulation. We know that there is a correlation between an increase in 0.1 Hertz 10 delta and a decrease in insulation breakdown voltage at power frequency. So the 10 delta is based on VLF technology. We will use a 0.1 Hertz VLF sine wave shape. We cannot use the cosine rectangular to do a 10 delta test. Must be a 0.1 Hertz VLF sine wave shape. It's a diagnostic tool, so we will have 3 assessment criteria: the mean value of the 10 delta, the delta of the 10 delta, and the standard deviation. And the results can be compared with the tables in the IEEE 400.2. And also is a prescribed test method by the IEEE 400.2 2013. Very important also for the 10 delta test, as we can use, as I said, the VLF sine. We must use the VLF sine, and the frequency must be 0.1 Hertz. We cannot decrease the frequency when we are doing a 10 delta test. We can do that in the VLF test, but we cannot do that when we are doing a 10 delta test. The frequency must be fixed, and it will be 0.1 Hertz. The parameters involved in the 10 delta test is the wave shape. The wave shape must be sine, as I said. The test voltage will apply 3 voltages steps: 0.5 U0, 1 U0, and 1.5 U0. This is according to the IEEE 400.2. The test time will depend on the measurements we took per voltage step. The IEEE recommends between 8 to 10 measurements per voltage step, so it will take around 15 minutes. And I said in the previous slide, the frequency must be 0.1 hertz. 0.1 hertz. We cannot decrease the frequency when we're doing a 10 delta test. What are the goals of the 10 delta test? Well, detect the aging conditions in the insulation of the cable. For that reason, we will do the 10 delta test in all cables, at least cables that have been in service for 5 years. The goal is to alert to critical aged cables before in-service fault and with up to 1 to 2 years notice. And of course, also to help target worst cables first. Now, let's continue with the third method, that is the partial discharge test. The partial discharge are little electrical sparks, and they eat the insulation of the cable. And generally, a partial discharge test, generally, I will say, is a non-reversible process. We have exceptions for this, okay? For instance, in the paper insulated cables, we have exceptions. But normally, in general, we will say that the partial discharge is a non-reversible process. Therefore, they will initiate the phenol cable fault. So how we do a partial discharge test? Well, we will apply a high voltage to excite the partial discharge in the cable and its accessories. We can use different wave shapes. For instance, we can use the damped AC. This is one of the wave shapes we can use. We can use also the cosine rectangular slope. Not all the wave shape, only the change of polarity is the slope when the change of polarity happens in the wave shape cosine rectangular. And also we can use the sine 0.1 hertz VLF wave shape, okay? We will measure the partial discharge activity in the cable. We want to measure what is the level of the PD activity in my cable, but also I want to localize the PD activity spots in my cable. As we can see in the graphic at the bottom of the slide, we can see that we have a cable of close to 6.5 kilometers, and we can see partial discharge in the phase A up to 20 nanocoulombs at the beginning of the phase A, and in the phase B and C, we can see close to 2 kilometers partial discharge in a joint. Okay, so this is the idea of the partial discharge. Not only measure the PD activity, the level of the PD activity, we want also localize the PD activity spots. What parameter we will measure during a partial discharge test? Well, the charge, of course, the amount of charge, the intensity of each dielectric breakdown, and we will typically measure in picocoulombs. It could be also that we'll measure in nanocoulombs, but typically will be picocoulombs. We will measure also the time the signal from the breakdown takes to reach the sensor, and then we will determine the distance to the partial discharge spot. We will measure also the voltage, the applied voltage. We know that there is a dependency of the partial discharge with respect to voltage. For instance, if we start to see PD activity at 0.8 U0 in the partial discharge measurement, and we increase the voltage, then the level of the partial discharge will increase. So for the reason it's important to see the relation between the voltage, the applied voltage, and the level of the PD of the partial discharge. Also very important is the partial discharge inception voltage, that is the voltage when the PD activity starts in the cable, and the partial discharge extinction voltage, that is the voltage when the PD activity stops in the cable. The goals of the partial discharge is to detect improper installation, manufacturer defects, and third-party damage. Nowadays, the partial discharge is mainly used to detect or to see for poor workmanship issues. It will provide an early warning of the incipient faults, and we will have the possibility of remedial repair or replacement action during a scheduled outage. So this is what is the goals of the partial discharge. And now we will continue with the next topic, that is the tan delta, best practices on tan delta, and it will be presented by Sergio Resso. Michael, if you can pass the control to Sergio, please.
Sure thing. Sergio, are you ready to receive presenter control? Oh, Sergio, we might still have you on mute.
Yes,
There we
I'm
are.
here. Okay.
All right. Wonderful. Presenter control is heading your way.
Show my screen.
Perfect.
There we go. And I think I erased the slide on accident.
Yep, we're okay.
So thank you, Javier. Thank you, Michael. Thank you, everybody, for joining us today, as my colleague has mentioned. So what we're going to do is go into when to use tan delta. Of course, it's typically used on age cables, 5 years and greater, and we also use this to detect aging condition change and dielectric properties of these said cables. So as you can see in this picture here, to my right, this is a cable tray with old cables sit into it, a service stage cable. It's also be used as part of the cable maintenance strategy. It's going to alert you to critically aged cables before in-service fault and up to 1 to 2 years notice. It's also going to be used as part of a cable replacement project, and where this comes into play is that it's going to let you target the worst cables first and allow you to have the best and wisest choice of the available money in which, depending on how valued that asset is, where you should spend your money first. Now we'll go into why to use the tan delta. Of course, this is a non-destructive test. It is very unlikely to fault the cable during or after this test. It's a diagnostic, so it can estimate the health of remaining insulation of an aged cable. And it's also to detect aging conditions and possible unclean accessories as well, albeit either a term or a splice. And then, of course, increase system reliability in the bulk insulation. What can it detect? It provides an overall condition assessment, estimate life lost in the cable insulation, and it can detect presence of water trees, contaminants in insulation moisture, degraded accessories, and oil leakage in PILT cables. If you look here at this picture, this is an example of a water tree in the insulation, and here's your semiconductive layer, your outer semicon, and your conductor, whether it be aluminum or copper. What it cannot detect is it cannot locate discrete problems, only that there is or is not a problem. As stated before by my colleague, this is a global assessment. What specifically the problem is, it cannot detect either. Is it a corroded concentric, a water tree, maybe a dirty term? Problems in the jacket or the lead sheath, poor workmanship, manufacturer defects, global measurement that does not localize. Basically, this is a leakage current measurement. Not basically, but that's part of what it is doing here. Theoretical approach is the simplistic purposes of the circuit represents a cable with a perfect insulation. If you look here, let me get into my animation here. If the cable insulation is perfect, then the resistor in my circuit, sorry, my webinar thing is blocking my words. Other words, and the value of resistance trends to infinite. This will mean that all the current in my circuit is a capacitive current, and then it is 90 degrees shifted to the voltage applied. As voltage here, there's my resistive, there's the infinite, there's angle, excuse me. Sorry. This is the, sorry, somebody's knocking at my door. Tan delta, represented here in this slide. Sorry, I'm going over to the next slide. Wave shape frequency. Sorry, we use a sine wave shape. Test frequency is at 0.1 hertz. Number of tan delta values, 8 to 10 per voltage step. Which voltage levels? Stepwise increase in voltage. So if you look here on the bottom right, step 1 is at half nu aught. Step 2 is at operating, and step 3 is at 1.5. Any questions? Okay, so why we need to use a sinusoidal wave shape. Here's the sinusoidal as you saw earlier. And then the difference is here on the right, the cosine rectangular, we don't have the phase reference between the current and the voltage in this cosine rectangular for the tan delta measurement as opposed to the VLF. And then in a purely capacitive circuit, the current leads the voltage by a 90-degree angle as applied here. A is the voltage, B is the current, and then this is the time. Going into this, you're always going to use 3 voltage levels. So the 3 criteria are how you assess within the standard. And that's key because you want to be able to have all 3 of these to be in the standard. And also furthermore on that is that different dielectrics, different types of cables will mask other problems. So if you look here, this is 0.5, 1 times, 1.5. This is the mean VLF TD. If you look at our animation, this is the 8 to 10 values on between each step. 8 to 10 values all between each step. And this is the equation. Here is the differential VLF TD, which is the DTD, as per IEEE 400.2. And then it says here, it's tan delta, the behavioral to increase the voltage. Look here, this is the average of those 10. Oh, sorry, I went a little too fast. This is the average between these here, and these here. This is your value for the DTD. And then VLF tan delta time stability, for the standard deviation, is the difference between each measurement, all 10 in between each step, is the standard deviation. As you can see on the scale as we grow up, this standard deviation is higher, and then so on and so forth. The assessment criteria is the measured values of the TD, DTD, and standard deviation are primarily influenced by the conditions of the cable system components. So historical figures, table 4 is the historical figures of merit for condition assessment of service age PE-based installations, e.g. PE, XOPE, and TRXOPE using 0.1 Hertz. So this is the table in the 400.2. As you see here on the left is condition assessment, no action required, further study advised, and action required. VLF TD, so this is actually backwards from what we've shown, but this will be the first slide. Mean VLF TD at operating would be less than 4, would be no action required. 4 to 50, further study advised. Greater than 50, action required. This would be our DTD, difference in mean at 0.5 to 1.5. Less than 5, no action. 5 to 80, further study advised. Greater than 80, action required. And then VLF TD time stability would be, of course, standard deviation. Less than 0.1, no action. 0.1 to 0.5, further study advised. And then, of course, greater than 0.5, action required. Assessment criteria. So breaking those each action down, no action required means no indication of severe problem in the short term. The cable system can be returned to service, and the cable system should be retested at some later date, maybe 4 years. Further study advised would be additional information is needed to make an assessment, comparing historical TD results of the tested cable system. This is important because historical would mean that you've done this more than once in an aged circuit, not new, in an aged circuit. An example of this would be maybe a cable run that before had a failure, you added a splice, and so you had the data before the splice, and then you would have it after the splice. Additional diagnostics test, monitored withstand test, visual analysis of circuit components, and then of course action required would be poor insulation condition. The cable system should be considered for replacement for repair immediately. This is voltage dependency of the tan delta. If you look here, this is just like we were discussing a minute ago. This is on time. If you look at our table here, you have the red reference cable, which is new, the yellow, which is slightly service age, the green is moderately service aged at 2 years, moderately service aged at 3, strongly service aged. So if you look here at this scale, voltage dependency of the tan delta of the new and service age medium voltage XLPE power cables important factor for decision-making process is the tan delta, also called tip-up. So if you look here at this 1.5 times of this aged cable, you can see here how this is dramatic jump up from the new to the moderate to the service age to the slightly. Oh, sorry. And this is where those the values come into play. So there we go. How to interpret results. So this is a report section of the tan delta. This far left representing the tan delta values. This representing the voltages at each step. And then this is representing of the phases in each set. So phase 1, phase 2, phase 3. And if you look, this is a tan delta on good cables. If you look how they trend between the voltage ranges coming up. And then how we're going to interpret results here. So this is the same cable. One is in the rain and one is in the sunny day. So if you look here at the voltage kV is 12.7 here, 19 here, 25.4 here. Excuse me. Phase 1, phase 2, phase 3, this is your tan delta value at each step. And if you look here, 589, 602, 711 represented by this blue phase here in L3. Then you see the same exact cable here on the sunny day now, same voltage range, 12.7, 19, 254. Phase 1, 338, 388, 500 as compared to 589 in the rain. Phase 2, 343, 394, 477 as opposed to 602 in the rain. And then phase 3, 369, 426, 497 as compared to 711 in the rain. So tan delta is a measure of temperature and humidity. It's also a factor in this. How to interpret the results. So if you look here, this is a wet cable. If you see phase 1 is green, phase 2 is red, phase 3 is 3. Same scale, tan delta and voltage. Now, if you look where this starts, when the cable is wet, see how initially it starts high here on phase 3, and then as the voltage is applied and increased, you actually see a decrease, letting you know that it is water. So that's what this cable does here under an actual wet. Limitations of tan delta. In order to meet the standard, the frequency, as my colleague mentioned before, must be 0.1 hertz for tan delta. If other frequencies are used other than 0.1 hertz, and we cannot use the tables of the IEEE 400.2 to evaluate the tan delta. Another limitation is the limited length of the cables under test, around 3 kilometers. And then another major factor is when measuring hybrid insulation types on the same circuit, i.e. you have some EPR, some PILC, maybe some of it is XLPE, and you've tied that in. The different insulations will mask the defects depending on what insulations you have in that circuit. And these are the limitations of all tan delta values. And of course, if you're not using the 0.1 hertz and the 3 steps, there's no table to compare to. The tan delta is a scalar quantity, dimensionless unit. The measurement is a function of temperature and humidity, as I stated before, and it's the measure of the loss angle, ratio of resistive and capacitive current. As cables age, the insulation of the resistance decreases, the resistive current increases, and the angle increases. Compare this angle to the IEEE 400.2 2013 tables, and you are able to make the proper assessment. Excuse me. What we have here is our product list for VLF sign units with internal tan delta. So here we have a 45 kV unit and a 62 kV unit. All of these units have a built-in standard assessment reporting already in these units. So these units not only have the VLF technology with the sine wave, they also have the built-in tan delta, so no need for an external missile type connection or extra connections to be able to have your tan delta values. And all of the reporting that we just went over is also built into the assessment report. So for the end user, this is great because as you introduce what cable you're at and the voltages you're using, the standard is built in and it'll give you an automatic assessment. So making that an even easier unit to use going forward with your technicians and looking at data. This is a VLF and TD test using a graph to show you how the connections work. So if you look here, here's our box. This is your power cord for this actual unit. Your grounding, which is going to be usually at your single point, whether it be at your transformer or your connection, your switch. And then this is your high voltage lead to your conductor, whether it be NEMA hole, load break, or dead break. And then the return, which is always right outside the termination where it enters out of the termination. And of course, this is your single point. And this very simply is the connections to be able to take these measurements. What we have here is the top of the screen looking down at these units. As you can see, this is your jog wheel. This is how you control, it's your mouse. It's going to allow you to go into all the functions of the actual unit itself. This is your e-stop. Number 2 here is your power. Number 3 is your key interlock for lockout tagout. Green is your power on. Red is your power off. Number 6 is your USB. And then number 7 is your screen, which looks like this. And this is the actual control panel that you'll be looking at. So if you hear it's a VLF Sinus 45 unit, it is a date and time stamp for you so that you never lose that data. It has the standard that you'll be using at this, in this particular is 400.2, 1.5 times. L1 action required. Of course, here's the VLF 10 delta, and this is your jog wheel as you use your mouse. It's telling you the phases that you've already done, that you're grounded, and so on and so forth. This is doing a 10 delta test. This is an actual data sheet. So once the test is done, of course, it's going to give you this automatic IEEE 400.2 standard assessment for you. Excuse me. This here is a report. Actually, let me blow this up. So if you look here at this report, this is the project cable information. So you can enter in your cable type, what it is, 1/aught, 220 mils, location, your start, your end, the voltages you're using, the phase you're on, cable size, so on and so forth. In your notes here, you can add obviously where your connections are, but also remember we were saying that tan delta is a function of temperature and humidity. You can put what the temperature and humidity is here too, so that as you see this data, you'll be able to know, was this actually affecting me? Was it raining on me? So on and so forth. If you look here, is this graph, just like we were showing earlier, but now it's in the report of this L1 phase. These are your voltage steps. And if you look phase 1, L1, voltage was 14.9, frequency was 0.1, capacitance was 43. Here's your average tan delta at 43.4. Delta TD was 52.9. Standard deviation is 0.71. Average tan delta result. And here it has all 3 of each phase or of each step. And your result, of course, is action required. And the criteria, it even breaks it down to as to what criteria you are going to. And the inspector or user as you like. Here's another look at those same things. So this is the action results as this whole system works. Okay.